This is Dr. Sivaji. We are going to discuss about the subject compiler design. In this subject, some of the problem solvings which are related to uh, runtime environment and type checking previously we have done. Now, some of the problems which are related to problem solving in type checking and runtime environment. Let us see some more problems in this one. See here, generally we performed a operation that is sort operation, quick sort operation with the help of type checking parameters. Now, how the partition can be done in this one? Suppose the parameters which are described for this quick sort is in this procedure. Quick sort is m and n are the parameters which are described in this one. We are going to verify whether this n is greater than m, because we are going to repeat this process until and then divide them into several partitions. Divide them into several partitions until last element is reached. Partitions until last element is reached. That means last element is reached means if the condition is true, we are going to reiterate some of the things, and then if the condition does not met, then it comes out. So does not met indicates that a least number of elements are reached, then we can come out and we can perform. So this partition algorithm is to be taken care of the two with m and n and gives the result I. Now this once again this I variable is passed. Once again we call it the quicksort procedure. Quicksort of m comma I minus 1 and I plus 1 comma n. So this is the range of integers from m to n. So m to n range of integers. So we are going to perform some division, that we perform the partition based on some element. So this partition can be considered as I. So before I, that means I minus 1, and after I, that is I plus 1. Take two partitions. Now we are going to, whenever we call the perform, that is quicksort procedure function, then it entering and leaving the this arrays. That means here quicksort 1, 9 invoked, then it enters that particular activation record is activating the procedure, the corresponding procedure whenever the control comes to this place, and after completion returns, then it leaves the corresponding partition. Similarly, next partition like this, there will be several partitions repeatedly occurring executions for all of the partitions until the algorithm terminates. So that is to be recorded out as a array of integer values with the corresponding procedures. That means the quicksort 1 comma 9 activates begins activation. That means started the procedure and execution takes place, and it comes out some result. That means before starting another, that means second one is leaving the procedure. So that entering and leaving can be described as a tree notation. This is called as the activation tree. This is called as activation tree structure. This is called as activation tree structure. In this activation tree, start node is the node, first node, that is start node yes, and that is start node or root node, we can say root node or root node. Then immediately we perform one that means m comma n, quicksort of 1 comma 9. That means there will be number of elements 1 to 9 integer values. There will be several number of integer values, that is 1 to 9. That's why q of 1 comma 9. Now this 1 comma 9 partitioned into 1 comma 3 and 5 comma 9. That means m comma I minus 1, I plus 1 comma n. So this partition after partition, see here this m comma I minus 1, once again partition with this 1 comma 0, 2, 3. This 5 9 once again partition 5 comma 5 7 9. So this partition and quicksort procedure repeats. Here it enters and leaves. That means it completes entering the procedure and leaving the procedure. 2 3 also partitioning once again. So here it reaches the end. That means 9 comma 9 3 comma 3. There is no further partitions possible for this course. So it terminates. It comes out because of the condition fails in the if condition. That just now in the previous we have considered the algorithm. So in this algorithm, see partition m comma n. Based on that partition, we are going to define quicksort of and then second partition. Like this, these two partitions will be available until the corresponding condition satisfies. If that is reached the corresponding end of the values means suppose 1 to 9, that means this partition takes place for 3 and this partition takes place, then 3 comma 3 is one partition, 9 comma 9. So if that end is reached the corresponding values, then it comes out. So like this, this is to be terminated with the several procedures activated continuously, and then that means each time. So at quicksort 1 comma 9 and the partition entering and leaving the partition 1 comma 9. Here in this case it enter the partition and then entering the quicksort procedure partition 1 to 9, and then after that again it goes to the partition. And then 1 comma 3 quicksort of 1 comma 0 2 comma 3. Again this goes to partition and then do partition, and then once again calling the quicksort invocation several times until this condition reached. So these are all written as a stepwise procedure. So this cannot be further division partition not possible because of the m greater than n. This is also further not possible. This is possible, but these two cases, this one also not possible. Here it is possible. That's why these three came. But here in the quicksort 7 9, these two partitions are not occurs because of the condition m greater than n. So we stop this procedure. And what is the result that is available can be supplied to this with this the help of this partition, and with the help of this partition that is to be supplied with this one. Because of these three combined with 5 9 attempts, because these three partition combined this result, and this 1 comma 3 5 comma 9 gives the result to the back 1 comma 9. So that's why as a series of elements 1 comma 9 it distribute. Now some of the element that is to be clearly verified what type, that means type checking, how it is performed in case of syntax directed translations. That means here some of the programmatic statements which are generating at the syntax directed translation, and what are the semantic action that is to be taken place. So this program consists of sequence of declarations. So D is declaration and E followed by expression. E is an expression. So here the program contains several declarations, and each declaration contains again some identifiers. T means either character, integer, type. What is the type? It is character type, integer type, array type, pointer. So character type it is type T, integer type, array type, pointer type. So that is to be mentioned as a semantic action while describing this information. Suppose if T is of type character, then the type checking performed T dot type equal to character. Here if that is not defined, then what is of type? ID dot verifies. There is a method called add type method. It accepts the parameter entry type, what entry type it is, that is T dot type. It clearly checks whether it is of type correct or not. So based on that it goes to the further step action. Integer T dot type equal to integer, array type T dot type array type, pointer type that is arrow, that is here also T dot type equal to pointer type. So based on these actions it verifies. What is the semantic action that belongs to an expressions? So this is a question that we can deliver. That is direct one is whether what are the statement of sequence of execution of the statements while performing an expression and what semantic actions it perform. Similarly, in case of expression, what are the semantic action that is to be considered for each of the expression where it contains array type, pointer type, mod type, and identifier, numeral, and literal. Suppose if it is a left hand side, what is the type of E matched with the character or not? In the second case, type is of type integer because it is declared as a num, so it is verifies with the integer. Third one is EID, that means the type of expression E is equivalent to the identifier. So identifier is to be verified in the symbol table. Symbol table, there is a method from the symbol table. We are going to use a method name that is called as lookup method. This method retrieves the corresponding values, and based on the retrieval of this value, what is the value that is to be retrieved can be compared with E dot type. If that is of same type, then we can say that it is valid. If not, then it is does not satisfy. Then it is not. Then other condition, false case we will consider. So true case where expression. So like that here mod integer also, both expression 1 and expression 2 is to be verified at the beginning is of type integer type. So here verification is e1 dot type integer, and the second expression is of type integer, and then after performing the operation mod, then what is of type result, it is also an integer or not. Suppose if other than integer specified, then the result expression is written as else type is a type underscore error. Type underscore error. So based on the value of the resultant expression after performing this operation e1 mod e2, then the result value of the expression is also specified. Similarly, if you consider the next rule, that is e derives e1 of e2. So here e2 is not this ordinary type. So the e2 type is generally in the within the index of this one. We are going to write, for example, a of 10. A of 10. So array of 10 integer values holds. So here in this array of integer holds, this 10 is of type integer values. That means how many 5 values, 10 values, 15 values. So the E2 expression, so this is an E2 expression. This is of type expecting is integer. So it can't be a 5.3 something like that. So it is of type into only. So this is verified whether the expression 2 is of type integer or not. Then the second one is E1. So E1 is of type, what is this one? This is this E1 means here array. So A means array type. What is the type of this one? It is an array type. Now this array type and integer type of this one can be correspondingly finally E dot type, that is matched the corresponding T, else errors are to be expected. Errors are to be raised. And the third one is pointer type, E1 arrow pointer. E1 up arrow. So here the type of E1 is a pointer and the type E dot type is T. E1 dot type is pointer type, then the E dot type equal to T, then else here it returns error. Then it returns error. So E1 dot type is a pointer type, E dot type is a T. Here pointer type is expected with the corresponding result. So the result is also of type T, else error. Then how the type checking action takes place for Aeronautical statement like assignment statement, conditional statement, while statement, assignment, conditional, while, and sequence. So S derives ID, S implies ID equal to I. This is an assignment statement. So here in this assignment, what is the type of identifier and what is the type of E? Both are to be verified. If they are equivalent or not, then has to be validated. Else error. But structure, what is the if then expression E of type? Is of type what? Is it Boolean, true, false? Statement 1 is of type. Then based on that, result is also hold some type. So S is of type what? So if the both cases okay, then performs work. Else it raises and type underscore error. While expression E. So here the while loop expression is to be verified based on the given condition, that is true or false. So that's why it moves to the S dot type. That means within the loop statements are executed based on this expression. So if not, errors, else error. That means condition fails, the error is associated. Now, for example, there will be several number of statements such as S, S1, S2, S3. Then individual statements are to be verified first initially. That is, what is the S1 is of type, and suppose S2 is of type what? So is it both are valid or not? So suppose if S1 is of type as an void, that means that does not return anything. S2 dot type also void, then both the cases. So then S type is also expected as void only. S type is expected void only. Suppose other than the void, any other thing is reached other than void, received, other than void result to the error. Other than void resultant to the error. So that's why it is written as else type underscore error. How the type checking of expressions and functions. Here the functions are also specified with a list of the value, that is here double x is one parameter, x with the type double, and y is also another parameter with of type character. Then the function checking of this one can be verified x into y, that is double into character. So that gives the result what is the return type. So E2, E1 of E2 indicates that E1 is of type expecting, and that is equivalent to E2 of type. Both, if they both are equal, then the E dot type expected is type T, else type underscore error. So in this case, we have seen how the type checking can be done for a simple language such as expression, that is character. Simple language means an individual statements with integer, character, float, array, pointer. Like this, the individual statements of each of the expression values, whether is of type identifier or not. And second one, type checking of expressions. That means this corresponding expressions, a given expression is suppose E literal, number, identifier, E1 mod E2, E1 of E2, pointer E1. These expressions are to be evaluated with the corresponding types. If the batch founds with the right hand side of the, suppose E1 dot mod E1 mod E2 perform, that means E1 mod E2 perform the result with the resultant with the performer, that is of type integer. Then the E dot type. So why? Because E derives E1 mod E2. Then E dot type is also expected of type integer only. Suppose if any deviation occurs other than this type, other than type, the corresponding type integer receives, other than type integer receives, then this returns error, type underscore error. Else it returns the corresponding integer type. So like this, we can found the semantic actions for the given statements like assignment statement, conditional statement, while, assignment conditional, while assignment means S derives ID equal to E, conditional means S derives if E then S1, while statement indicates that S derives while E expression do statement 1, sequence means list of statements, that is S derives S1 colon S2 S3 so on like this. And then the function of functionalities, type checking functions such as a ordinary function which takes the parameters x and y. The result of this one is also verified with this the corresponding type. So now not only that is, we have seen some of the semantic notations for the corresponding expressions. Now in this problem solving of type checking, sometimes the declarations may also go in and out of the bounds. So that is also to be verified clearly. In this, what is the scope of the variable? In this example, what is the scope of the variable that is defined inside the blocks? So what is the declaration which you have declared? That is A is one declared A equal to Z. 0 B is of type another integer which is declared. Here B equal to 1 which is declared of type. Next A equal to 2 is also another type. Next B equal to 3 is also declared. Now A equal to 0, B equal to 0, these two are defined at one block, that is main block. That means here the blocks are defined as B0 and B1, B2, B3. Why? Because if these variables belongs to this block, if these variables are belongs to this entire block, then B0 to these variables belong, that means A equal to 0, B equal to 0, both are belongs to the blocks, that is B0 block, B1 block as well as B2 block. So B0 to B2, these are to be considered. The scope is to be available. But B0 to B equal to 1. So that is to be available in B2, B equal to Z1. B1, why? Because this block is defined within this one. So B equal to 1 is defined with block B1, block B2, block B3. So from B1 to B3, this is to be defined. Whereas A equal to 2, but A is equal to 2, this is limited to B2 only. So this is available in block B2 only. B3, B is equal to 3, this is also available in block. Now, that's why here, what are the variables which are occurring this outside can be not within the scope. This is outside the scope. That is, and the accessibility is only inside the scope. So that's why this A equal to 2, which is limited to block B2, accessible within this block. B equal to 3 is limited to the. So sometimes we need to verify whether the declaration is several times or multiple declarations within the same block also. So we are going to verify multiple blocks. In case of multiple blocks, verify the declarations several, how many times it is, multiple times, or with inside the block or outside the block. And scope, it is limited to block B1. So in this example, B0, B1, B2, B3. So which block, up to which block the scope is limited, and under which circumstance it is defined. So that is to be verified with the help of this type checking environment, the help of runtime environment. In the case of components and runtime environment also, these checkings are to be done clearly. And if any violation happens, then it reports an error mechanism based on the scopes. So like this, we are going to define scope and further variable notation, whereas the syntax and semantic rules which are applied for these notations, for example, simple language notations, and also expression type notations. And third one is statements, individual statement notation like assignment, conditional, while, and sequence type of the notation. And also as a type checking of the functions are also we described as. So this type of notations where we describe the types are assigned, that is expression of type matching, that is equal to the right hand side the assignment, that is the expression of type E1 and expression of type E2 compare, and result comparisons that can be written as within the curly braces. These expression types are to be written. That means these types are called as the dot attributed associated values, where the evaluation of the corresponding values results yields the corresponding the matched result with the right hand side of the given rule. Then we can say that it is a if the type is matched. Else, then it returns an error, that is type underscore error message. So like that for each rule, we are going to define with a semantic action. And also whether we have also seen in the previous session whether these types are exactly matched with the corresponding left hand side with the right hand side. So see, here we have seen the semantic actions. In the previous session we have seen the matched types are also equivalent or not, that is name equivalent, structural equivalence also we have described in the previous session. Now this is the different problems which are available in the type checking and runtime environment of this phase of the compiler design subject. Now the things which are related to these problems which you can find from the book, that is Compiler's Principles, that is written by Alfred Sitte and Wellman. At the time permits, then today we are starting. Next session we are coming with a new problem solving techniques with code optimization and code generation phases. And now today, thank you very much for giving the opportunity to deliver this session. Thank you. Next time we'll come with a new topic in the another phase of last phase of the computer design subject. Thank you once again. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.